Hello and welcome to today's video lesson where we're going to talk about Le-Chatelier's principle. We're going to focus on changes in concentration today. Now there are a variety of other factors that can influence a chemical reaction, but we're just going to focus on concentration for this video. So we have our equation shown here. This is called the Haber process. So nitrogen plus hydrogen gives me ammonia. It's in equilibrium already. And what we want to see is what happens if we modify the concentrations of the different components of this reaction. So Le-Chatelier's principle says that whenever we add a stressor or whenever we change a variable in an equilibrium equation, the reaction is going to want to compensate for that change and go back to its original state. So let's look at these examples. For question A, if this reaction above is at equilibrium, if I increase the concentration, square brackets, remember that means concentration. So if I increase the concentration of nitrogen gas, what is going to happen with my chemical reaction? Okay, so let's take a look. I like to actually mark up on the equation. So if I increase the nitrogen gas, then that means this concentration is going to go up. And if you look at my diagram on my equation, what I see is that I've got more reactants now. So there's a greater likelihood for nitrogen to collide with hydrogen. This is, by the way, part of collision theory. So if nitrogen's concentration increases, what we can say is that there's a greater tendency for the equilibrium to move to the right. So the equilibrium here will shift right towards the products. Now again, the reason for this is because when I increase the concentration of a reactant, there's a greater likelihood of collisions because there's more molecules now here on the left side that will cause a greater chance of collisions, causing this reaction to move this way to form more products. Again, it's compensating for that change. As I increase the reactant, they're going to react and they're going to create more products as a result. Okay, now let's try the next one. So if we increase the concentration now of our product, NH3, what is going to happen to my equilibrium shift and why? So on my chemical equation, let's draw an arrow upwards on the ammonia, and it's going to, again, its concentration is going to increase. Now there's 2 moles of ammonia on the right. So the products, because there's more of them, there's a greater chance that they're going to react with each other. That's going to cause the equilibrium to shift this way to the left, going back towards the products. So in this example, for question B, we're going to say that the equilibrium shifts to the left towards reactants. Okay, and that again, it has to do with collision theory. There's a greater chance of your products colliding and reacting now because you have more of them. Okay, now what about our third example? So if we decrease the concentration of hydrogen gas, what's going to happen? So if hydrogen gas decreases, think about the logic. I now have less molecules on the left side. So over here, there are less reactant particles or molecules to collide with one another, which means that the forward reaction is actually less likely. When I remove a reactant, the system wants to replace the reactant that we took away, and there's just less of them to collide. So as a result of this, we're going to move to the left again. So the answer here is that the equilibrium will shift to the left, again towards the reactants, because first of all, the reactants, you don't have as many of them to collide. So as a result, there will be more product collisions, which will move your equilibrium backwards. So that is how we tackle a scenario analysis with changes in concentration. And let's just do one more thing in this video, which is to look at a graph analysis. So same question where we're going to look at the change in concentration over time for a equilibrium reaction. So let's say I have N2O4 producing 2NO2. So I'm going to sketch a graph. By the way, a product in a chemical reaction, its concentration will always start at 0, and the products will always increase over time, right? So my products are going to go something like this, and then I'm going to level off the concentration to show that it'll eventually get to equilibrium. So this blue line that I drew, that represents my NO2 product. For this equation, the N2O4, we're going to draw, I'll change the color here, we'll draw this as a yellow curve. So because this is a reactant, it always starts with a high concentration, and it will decrease over time, and then it will also level off, so it will establish equilibrium. So as you can see on this graph, where my 2 lines, like for example, where the 2 concentrations, where they level off and stop changing, that is my equilibrium state. So let me just actually mark it down. So let's make a little line here and say that equilibrium is established around here on this graph. Okay, so equilibrium is established and then equilibrium, goes on for a little while. Now let's say I introduce a stressor, a Le-Chatelier stressor of concentration. Let's say I change the concentration of something. So let's go ahead and actually increase the product. So let's say the concentration of NO2 increases. I'm going to draw a little line on my graph. I'm going to spike this upwards to show that I've increased my product, and that's the stressor that I've applied. So let's label this. Let's call this our Le-Chatelier stressor. And that is the concentration of nitrogen dioxide that has increased. So when the product increases, what's going to happen is there's going to be more product collisions, which will cause the equilibrium to shift to the left, and the system is going to want to reestablish its equilibrium state. So because I'm shifting my reaction to the left, the product NO2 is going to slightly decrease, and then it's going to level off. And then my reactant N2O4, remember we're moving to the left side. My reactant N2O4, this is going to increase slightly as well, and then reestablish an equilibrium state. I didn't draw that too well. Let's try that again. So this is my equilibrium. It's going to increase slightly, and then it's going to reestablish that equilibrium state. So if I want to mark up on my graph again, let me say that, okay, so again, this was my stressor. This is where I added a change. As a result of that change, my equilibrium moved to the left. So here, this decrease of product, this increase of reactant, this represents my shift. Okay, so this means shifting to the left or towards reactants. And same thing you can put on the top arrow as well. And then after that shift occurs, we can draw another dotted line here to say that equilibrium is eventually re-established. That's how we do a graph analysis on concentration stressors, and that's how we just kind of tackle concentration changes in general of chemical equilibrium and Le-Chatelier's principle. If you would like to see another Le-Chatelier principle lesson using a different variable like pressure or temperature or catalyst, please let me know in the comments, and if there's any other topic you would like to see, please let me know. Thank you very much for watching and have a great day.